Hello, everyone. My name is Xiaotian Zhao, a first-year PhD student of ICAS Lab at Shanghai Jiao University. The title of my presentation is TILE-MPQ, Design Space Exploration of Tightly Integrated Layer-wise Mixed Precision Quantized Unit for tinyML Inference. This is the outline of my presentation. Firstly, I will start with the background and motivation of our work, and then I will summarize our main contributions and explain our main methodologies. Next, I will describe our experimental setup and the results. Then I will introduce some extensions of our method. Finally, I will conclude my talk with a quick summary and our ongoing work. First, is the background and motivation. And in the recent years, we know that deep neural networks have made breakthroughs in image processing, target detection, neural language processing, and other practical problems. However, the primate number in neural networks is growing exponentially. So how can we put more accurate models into the small chip? It is a huge challenge for edge device. But maybe you will ask, why is this a challenge? Because the tinyML means limited computing resources and the less memory and limited power consumption. So how to put the model into the edge device? Can we compress the model into a small size? The answer is sure. Quantization is one of the approach that is very promising to address that problem. Okay, the quantization is a workhorse for efficient inference. The way that quantization works is very simple. A uniform quantization is a mapping from floating point values to the quantized integer values. For example, the matrix above is a pre-quantized model with floating point 32 data type, and after quantized, the matrix below is a quantized model with int 8 data type. Even though the uniform edge quantization have a reduced model size and speed up the inference, as the demand for the inference speed up keeps increasing. So can we further compress the model? The answer is yes. Mixed precision quantization is a good method to further optimize the uniform quantization. And in the MPQ, which is mixed precision quantization, we can keep sensitive layers in higher precision and apply low precision quantization to insensitive and inefficient layers. And in this case, we can improve the accuracy of the model as much as possible with limited computational resources and make the model size smaller and faster. So today, there are many works of MPQ method. However, in the existing works, there are some problems. First, most of them do not have the hardware support, and they only focus on the accuracy. And many of them use the NACE and the reinforcement learning to search the quantization combination, which is more accurate but very hardware resources consuming. So we want to make some optimization on it. Firstly, we propose an efficient architecture to support the quantization through tightly integrated in the unit in the processor pipeline. And the actual hardware awareness of quantization is measured by running the real inference with this architecture. Secondly, the proposed search algorithm aims to optimize the hardware and accuracy simultaneously. The optimization, the target has been redefined. And thirdly, the MPQ policy is light and more explainable. This is achieved by narrowing down the search space through a thorough study of layer-wise sensitivity. So then we talk about the main contributions of our work. To solve the problems we talked before, we propose the TILE-MPQ, which is a mixed precision method that tries to balance the trade-off between accuracy and hardware consumption. In this method, we have four main contributions. The first one is that we propose a new metric that takes considerations of hardware, and then narrowing down the search space. And the third part is we tightly integrated the quantization policy as part of the processor pipeline through ISON and microarchitecture code design. And the fourth part is our evaluation. It is worth mentioning that our algorithm achieved up to 11% higher inference accuracy with similar hardware cost compared to other SOTA MPQ strategies. Then we will have a detailed discussion of our method. So to explore the relationship between the accuracy and hardware consumption, we use BOPS, which is bit operations, as our hardware consumption proxy. We perform a brute force DFS search on the post-trained ResNet 18 ImageNet. We selected 6 layers out of the 48 total layers of ResNet 18 and quantized those layers to either int 8 or int 4 bit. We record the accuracy and the BOPS and obtain the figure. In this figure, the x-axis is the BOPS and the y-axis is the accuracy. We can find that the red line is a curve of the accuracy and BOPS, and it does not follow a linear relationship. And the blue box shows that the same BOPS values correspond to different accuracy levels, even though they have the same number of quantized layers. From the above observation, we can conclude that the certain layers show a stronger impact than others. So how to find the sensitive layers and how to find the optimal models. To solve the problem and balance the trade-off between accuracy and hardware consumption, we propose a new metric called W to measure such impact and sample the sensitivity of accuracy and hardware cost. We define the delta BOPS as BOPS 8 minus BOPS 4. This BOPS 8 means the data type of this layer remain uniform 8, and the BOPS 4 means the data type of this layer has been quantized to int 4. The same as BOPS, the delta accuracy means accuracy 8 minus accuracy 4. So inspired by the numerical analysis, by dividing the difference of BOPS by the difference of accuracy, we obtain the value of W. The larger the value of W, the higher priority this layer can be quantized with lower bit weights. So now we have the sensitivity metric W. So we apply W to each layer of ResNet 18 and the MobileNet V2 respectively. As we defined before, the taller bars indicate that the layer are most likely to quantize to the priority queue. We can see the ResNet 18 first. In each stage, the W of convolution layers are increasing, and the last few convolution layers have higher W of the network. This is in line with the network architecture. And we can see that in the MobileNet V2, it shows that the point-wise convolution layers are less sensitivity compared to the depth-wise layers, which is the bar is taller than the depth-wise convolution layers. This is also in line with the MobileNet network architecture. We now obtain the sensitivity of each layer of the model. But if we want to make a fine-grained quantization combination selection, so how can we do? To solve this problem, we propose a greedy algorithm. In this algorithm, we perform layer-wise traversal and keep selecting the layer with largest W in the current situation and put them to the quantization queue until we meet the hardware requirement. Finally, we obtain the number of layers to be quantized under this constraint, like the figure. Now we have the quantization combination, and we want to apply it on the hardware part. This is the quantization model and the quantization policy through the PyTorch we obtained. Then we can generate the VMM custom instructions through the modified TVM. Next, we can map it to the VMM unit. In this unit, we can see that it supports different data type like int4, int8, and int16. For example, the int4 have more memory for computing, so it will have a faster inference speed than int8 and int16. To further justify our choice of BOPS as a hardware proxy, we compare the ratios of CPU cycles and the BOPS. We can see that they share the similar ratios, so we can believe that the BOPS really makes sense as a hardware proxy. Then I will talk about the evaluation and the result of our work. This slide shows the setup of our experiment. We use the ResNet 18 and MobileNet V2 as our test model because they are light and suitable for the edge device. For the quantization method, we mainly use the PTQ instead of the QAT because the PTQ is less time consuming and the hardware resources consumption. We use the ImageNet as our data set and the NVIDIA GPU as our hardware platform. This is the evaluation result of our experiment. The first table is our algorithm test on the ResNet 18. We can see that there are 3 different BOPS levels, which is high, mid, and low. For different BOPS levels, our method all have higher accuracy than the SODA strategy HAWQ v3. Then we want to make more creations, and we expand the bit weights from only int4 and int8 to each bit between int4 and int8. We observe that for some models, like we highlight there in orange, it will have accuracy improvement. To further verify the generalization of our algorithm, we tested it on the MobileNet V2. And we also found that our method have a higher accuracy than the SODA method HAWQ v3. Although we mainly target for the PTQ, which is a post-training quantization. We also do an experiment of QAT, which is a quantization aware training to make fair comparisons against other state-of-art MPQ method. And we still achieve reasonably high accuracy with similar or less BOPS like there. Now we want to make some extensions of our method. As we discussed before, we mainly focus on the PTQ, which is the post-training quantization. It is only needs inference for every time. And instead of the QAT, which is quantization aware training, this method needs training for every model per time. So for a deeper analysis, we compare the QAT and bit PTQ. We define a new indicator P. This value is this blue line is the accuracy baseline without quantization, and this orange array is the accuracy degradation during the quantization. The value of P is the training model accuracy minus the inference model accuracy. We think that the value of P can reflect the degree of a model influenced by training. So to evaluate the indicator P, we selected some models and have some quantization combinations and calculate the P and plot the figure. We can see that with the increasing of the model, the value of P also increases. But we can also find some outliers like this red point, and this red point. We think that those models are highly influenced by training. So we analyzed those special models and conclude them in this table. Those outlier models are model 25, model 4, and model 11. we think that they do share some commonalities. So because we can see that those RAID models have quantized the same layers, like stage 1 unit 2 quant act 1 and stage 3 unit 1 quant convolution batch normal 1. So we think that they have some commonalities, and I will do a deeper research on it. Then I will give a quick conclusion and introduce our future work. In our work, we have proposed a new architecture to support the mixed precision quantization via tightly integrated the inference unit. And then we propose a novel search strategy for the optimal layer-wise MPQ scheme. And the proposed strategy are light, mass-proven, and explainable. It is also worth mentioning that our evaluation result outperform the state-of-art MPQ frameworks and can support different AI models. And in the future, we also want to make some optimization on the hardware part, because we want to obtain the PPA, which is the power, performance, and area effects from different MPQ policies, which will be quantified with the integrated inference unit. And we also want to develop a software and hardware co-optimization framework to further optimize our quantization methodology. Yeah, this is the reference, and thank you.
Well, thank you, Xiaotian. So this is a first-year PhD student. Very impressive work. Okay, all right. So let's try to answer some of the questions. So from Antoine, he asked, how do we know which layers are inefficient or insensitive layers?
Okay, that's a very good question. We know that in this slide, if the bar is taller, we think that it is not very insensitive. It is very insensitive and inefficient for the quantization. And if the W is very smaller, we think that it is sensitive and efficient. It is sensitive to the quantization. So we will not quantization those layers first. We will quantization those layers with a higher W values. Yeah.
So essentially use your definition of W, you evaluate each layers and compute whether that's sensitive or not. Okay, all right, cool.
Yeah.
And on these slides on the mobile nets, so it seems to me that you are per layer optimization, right? So for each of the blocks, you look at depth-wise, you look at point-wise, all these layers, and for each layers. So one of the questions I have here is, if you do each layers, so your activation map have to have the same quantization, right? Otherwise,
the same quantization.
Yeah, quantized bits for activation have to be the same for point-wise and depth-wise because they are consecutive, right?
Yeah.
And so if I want to understand, your activation is all 8 bits, and then you optimize the weights in your exercise. So activation map is that 4 bits or 8 bits or other bits?
In this figure, we only have 2 quantized levels, which is int 8 and int 4, but we have extended it to other bits, like every bit between int 8 and int 4. I don't know if I answer your question.
Yeah, but your quantization is only on weights, or is also on activation?
We on both the weight and the activations.
Okay, all right.
The blue bar is convolution layers, and the orange bar is activation layers. We analyze it respectively.
Okay, cool. So if nobody asks question, let me ask another question. So you must know that MIT have a work called HAQ. Can you comment on that?
Yeah,
that's right. Can you comment on that, the comparison of their work with yours?
Yeah, we also have some comparison between their work and our works, and we can see that in this figure. Maybe I can use this figure as an example. They use method of NAS search, which
That's
is
right. Yes, yeah, NAS based.
Yeah. But our method mainly focus on the math-based, which is I want to have a light and explainable method. But we have we share some commonalities between their works, and we also can use their works to prove our work is correct. For example, they also have the result that the pointwise convolution layers will quantize the first, and the depth-wise convolution layers will not be quantized first. And we think that we have the same conclusion. Yeah.
Okay, from different angles.
Yeah.
All right. So I do have a last question. I have time. So batch knob. So how do you handle batch knob in this case? Because if you for both ResNet as MobileNet, there's every layer have a batch knob. So do you fuse those and then do this quantization? So how do you handle the batch knob?
Yeah, I added the batch model. The background of our methodology is we use a platform of the HAWQ v3, and in this method they combine the convolution layers and the batch normal together, and we also have the
right.
Yeah, and we also use this method. Yeah.
Okay, so essentially you do fuse first, then you do quantization of different bits, and then after that, I assume you do QAT, right? Quantization version. Okay, understand. Yeah, thank you for explanation. I think there's no further questions, and this is probably end of the conference. Nick, I guess I go back to the conference chair.
A final thank you to our sponsors. So once again, thank you, Edge Impulse as a premier sponsor, Qualcomm, Syntiet, DeepLight, ClickerTech, Renaissance. Actually, what I'll do is I will go through because it will cover all the sponsors in detail. So the premier sponsor, Edge Impulse, for those who have like to try a simple approach to, I guess, development on tinyML devices, Edge Impulse is a great solution for you. Executive sponsors, Qualcomm AI Research, again, a great organization that has most of the chips in most of the platforms around the world, and as well as some of their new software applications. Syntiet, making Edge AI a reality. Platinum sponsors, DeepLight, fastest video analytics solutions on ARM CPUs. ClickerTech, global IoT solutions. Renaissance, I guess, enabling a next generation of AI-powered solutions that will revolutionize every industry sector. Sony Semiconductors Corporation. Gold sponsors, Analog Devices, where what if becomes what is. ARM, again, ARM, a large chipset provider as well, and they also have their own social nights, which you can join if you want to be more involved in the ARM community. PhotoHub, making over-the-air firmware models updates simple and accessible, especially important with all the sensors that require updates. Microsoft, providing, I guess, edge computing and the capabilities to integrate into edge or IoT or tinyML solutions into the Azure platform. NXP, again, a great hardware provider which integrates with the tinyML solutions. SenseML, an analytics toolkit suite for I guess, tinyML. STM Microelectronics, which provides extensive solutions to make machine learning easy. Engineering exceptional Synaptics, engineering exceptional experiences. And silver sponsors, AOZip, Aeon Devices, EMSA, Greenwaves, Gravity, IBM, Imagimob, Itermis, Nota AI, OctoML, Prophecy, Quexo, Rexon, SAP, Silicon Labs, Stream Analyze, TDK. I guess before I finish off though, if people are interested in sponsoring, please reach out to the team. We're always happy to have more sponsors, because it's with this sponsorship we can run such events. I just want to say a big thank you once again to the whole team, and thank you once again to the people who presented. Your content is key to making these communities grow. We're hoping next year we can have this in person. Don't forget, as we mentioned earlier, next year we'll be having the summit in San Fran. But thank you for all your help, and hopefully see you at the next tinyML session. Thank you, everyone.